Welcome. In this video, I'm going to go over another related rates problem. Observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. As is the angle of elevation of the balloon increasing 30 seconds after launch. Who are in my online class and have seen the other video might notice that there's a lot more to this example than the previous examples. So let's go over some steps. What we're going to want to do is sketch and label the scenario. So sketch and label. So I'm going to start with a sketch of the ground. There it is. And my observer is right here. She is. And now a hot air balloon. And that was a little trickier. So I actually sketched that before the video. The sketch of the hot air balloon. Now the balloon is rising vertically. Rising up in this direction here. Vertically at a constant rate of 4 meters per second. And we know the observer is 200 meters from the launch site. So this distance here is 200 meters. And now we're interested in the angle of elevation. Here's our goal. How fast is the angle of elevation increasing? So I'll write down this goal. That's really important. Our goal is the angle of elevation, so the change in angle over time, d theta over dt. Now, to achieve this goal, we're given a few things. One of them is 4 meters per second. We're given this 200, but we're also told we want the change in the angle of elevation 30 seconds after launch. So theta over dt when t equals 30. Let's finish this sketch now. There we are. And this is the angle of elevation. We have completed step 1. We've sketched, we've labeled. Let's think of any relevant formulas now. So that is step 2, relevant formulas. Well, I know I am interested in the rate of change of this angle. I'm given the length adjacent to that angle, and I'm given a rate of change opposite to that angle. And when I hear opposite adjacent, I think tangent. So the formula I'm going to use is tangent of theta equals opposite adjacent. Imagining this on an x and y axis. X, and this is y. We can call this here, or this one here, that's the x value. And this one here is dy over dt. So the rate of change in y with respect to time is 4 meters per second. All right, so this is dy over dt. And this is x equals 200 meters. Let's consider, is anything fixed? And actually, I should label this relevant formula here. Is tangent of theta equals y over x. And that is assuming this is the x-axis again, and this is the y-axis. So this is the rest of number 2. Next, balloon is going up. Observer, their angle here, as they're looking at the balloon, is changing as the balloon gets higher and higher. So the balloon would start off here, and you can see how the angle of elevation changes in this direction. So that's not fixed. The observer is standing still, so this distance is fixed. X equals 200. Fixed. So this is 3. Now I can rewrite this formula as tangent of theta equals y over 200. Have we used all the relevant information? Or are we missing something? Next, we want to use implicit differentiation. Consider if we're missing anything. So this is kind of an interchangeable step. Any info missing, and you'll see what I mean soon. Implicit. That's step 4. Go ahead and use implicit differentiation. And I should make that really clear. This is implicit differentiation. And we want d over dt, so the change with respect to time. So of tangent is secant squared theta, then d theta over dt equals the derivative of y is just 1. So this is dy over dt times 1 over, you can see here, dy over dt is d theta over dt. What theta is. Okay, so let's finish this up. Let's figure out what theta is. P equals 30. What is our triangle going to look like? Remember, this is fixed here. 30 seconds. 4 meters per second up in the air means the balloon will be 120 meters in the air. If the balloon is 120 meters in the air, then the tangent of this angle is 120 over 200. That simplifies to what? 12 over 20, or 3 over 5. So theta is equal arctangent of 3/5. Calculator, this will give you, in radians, oh no, excuse me, 5404. Okay, so that's what theta is. So now we can solve this. I know that d theta over dt is equal to dy over dt times cosine squared theta over 200. Remember, just 1 over cosine, in this case cosine squared. So all I've really done is multiply cosine squared to both sides to eliminate secant here. Theta over dt is equal to 4 times cosine of 0.5404 squared divided by 200. Please take a moment and pop this into your calculator. And if I were you, I would use the exact value from your calculator, so more decimal places, not this approximation. And make sure your calculator is in radians, by the way, radians. All right, you should get d theta over dt is approximately 0.014706 per second. A little weird, but remember, if you multiply a radian, 180 over pi, you get a degree, or you get an answer that's in degrees. So let's go ahead and do that. Oh, and actually, I didn't list step 5. Step 5 was solve. And we're doing that here. We're solving, and then we're explaining. So then d theta over dt, multiplying this on your calculator by 180 over pi, getting about 0.8423 degrees per second. Of elevation is changing at about a rate of 0.8423 degrees per second. It's after launch. I hope you found this video a pleasant excuse. Some cutesy looking hot air balloons, and of course learn some calculus.